next bit is set, and that means we shall have, this is 4, this is 2. So our next value that will be compared to our V in will be 4/16 plus 2/16, and then multiplied by 5. His calculation times 2/16. So that will be 1.875, and you'll find that our 2 is greater than the 2 is greater than this 1.875. So we have, if it's greater, then this is 1. So we maintain that 1. And then finally, remember that we have 4 bits, so we take the last one, and it will be 4/16 plus 2/16 plus 1/16 multiplied by 5. And this will give 1/16. We shall get our value as 2.1875. So we are comparing 2, and you can see that it's less than 1. That's less than 2.1875. So this is great. This is less. So we have 0. So that means the value that we get as the ADC or the digital number to represent 2 will be 0, 1, 1, 0 in this case. So basically, that's how the successive approximation happens, and it happens for each and every bit. So if you have like a 12-bit resolution, you'll have to do it. It does it 12 times to get the approximated digital value. So if we look at the STM32 block diagram, you will see that for the STM32 F4 that I have, we have 3 ADCs. We have the ADC1, the ADC2, and ADC3. And you can see that this operates at VDDA. And we have 8 channels that are common to the 3 ADC. So you'll find that one pin can be mapped as a channel from either ADC1, ADC2, and ADC3. And we also have 8 channels common to the ADC1 and ADC2. And then we have 8 ADC input channels to the ADC3. And just to point out is that the ADC clock comes from the APB2, which runs at a frequency of 90 megahertz maximum. So a few features to note in the STM32 about the ADC. We have configurable resolution from 6-bit to 12-bit. So that means if we use the 12-bit, the highest number that we could get is 2 to the power 12. And this should be 1490. Let me see, 2 to the power 12. So this is 1496. So you can get 1496 different numbers. That is ranging from 0 to 1495. So for the 6, just do 2 to the power 6. You can get 2 to the power 6. That means it's 64. So you can only get numbers or values from 0 to 63. So it's also important to note that the interrupt generation at the end of conversion is available because every time that you start the ADC in interrupt mode, you get a notification that the conversion is complete. You can also get this for injected conversion modes. You'll see how to configure this later. And we also have the analog watchdog timer in the ADC that keeps watch for the ADC value. You can just set the maximum and the minimum values of the ADC so that in case the values goes above or beyond the set window, then the whole system will reset. So we have different modes of conversion. We have the singular or the single and the continuous conversion modes. We shall look at this in the next slide. And just to point out the important things is that you can have scan mode whereby you have more than one channel, you can scan through all the channels and get to read the ADC from each channel. So that for the data alignment, we have two. We have the right and the left aligned. And the ADC comes with programmable sampling time, or this is the cycles. You can configure the cycle of each channel. So we'll also see this in a few. So we also have access to external triggers that can start the ADCs. We have the timers, we have the external pins that whenever you configure these pins or the timer interrupts, it can just restart or keep restarting your ADC so that you can get values. So you also have the discontinuous mode, whereby if you are taking some measurements from the ADC, it's only done once. So if you want to maybe get another ADC value, you have again to start the ADC and do the polling things, and then get to read the values. So another thing to note is that the ADC input range, we have the V-in that you want to measure. Remember that the V-in is measured with reference to the VREF. And where you are using the single-ended means that one side is ground, another side has been connected to the VDDA, 3 volts, and make sure that the V-in is not greater than the VREF. And this explains it better. So you can also configure a DMA request for the ADCs just to transfer data directly from peripheral to the memory, and this reduces the CPU overhead and leaves the CPU to focus on other tasks. So the ADC modes, we have the single channel, single conversion. So you start one ADC from channel X and then you stop. So maybe an application of this is whereby when booting the system, you can check if the battery level is okay or within the acceptable range. And then if it's okay, then you can continue to the main code. If it's not, you can just shut down the whole system or alert the user that the battery is low. You also have the single channel continuous conversion, whereby you start the ADC and then you get the values from the ADC channel, and then this keeps running by itself. So we have the scan with single conversion. So the single conversion and the scan, so we have so many different channels, and you can just get the readings from all the channels at once and then stop. And we also have the scan with the continuous conversion, whereby this we have so many channels. You scan through all the channels, and then when you get all the values, you get again to read all the channels. So this could be a system whereby you have some sensors reporting to the system, and you just want to make sure that all parameters are okay all the time. So just have to keep checking the values, and then if one value is out of range, maybe you can notify the user. So let's look at the single ADC block. Just open it from here. And this is the block diagram of a single ADC block in STM32. And maybe I can start from here. You can see that we have the VREF plus positive and the VREF negative. So this will help you when you want to provide your own external reference, and we call this mode differential mode. We also have the VDDA and the VSSA. In case you're using the single edit, this is what will be configured as reference voltage. So each channel has 16, each ADC has 16 channels, and you can see that they are connected to some pins, configurable pins, and together with the sensor, the temperature sensor, the VBAT, the VREF, they are all multiplexed together. And you can see that we have the injected channels, which are up to 4. And we also have 16 channels, that is regular channels. So this is the whole block diagram of the analog to digital converter, whereby it takes in the ADC clock from the APB2, then you provide a prescaler, then with this ADC clock you get the samples. So to point out is that we have the J external cell, so it's just a selector to help you trigger the injected group. So if you have you have configured a channel as an injected channel, then you can keep retriggering the channel using one of these options, the timers, channel 4 for BWM. So you configure the passes so that when the pass is complete, then you can trigger the ADC channel and get your reading. So you can also see that we have an external pin provided to us that you can also press and get to measure the ADC. So this is for the injected channel. For the regular channel, it's also similar, has similar operation, whereby you can configure different timers to trigger your regular channel so that you can get the ADC readings. So up here, you can see that you can configure DMA request to get your readings from the sensors to the memory. So for the regular channel, we have 16 bits. That is the data register. And you can see that all these regular channels share the same data register. So it's upon the programmer to know how to get, if you have more than one channel, that is a regular channel, it's up to you to know how to get the readings from other channel. And you can do this easily using the DMA or the interrupt method. So for the injected channel, you can see that we have all 16 bits registers. That means that each of the injected channel has its own data register. So up here we have the analog watchdog, which you can set the high and low threshold just to make sure that your voltage or your reading falls within the acceptable range. And we have several flags that can notify you when there's an error. We have the DMA overrun. So for the DMA overrun, overrun means that you have read data from the peripheral, and before it's transferred to memory, another data is copied to the same memory. So this will lead obviously to data corruption, or you might end up even reading the wrong data. So there's this register that you can check. If it is set, it means there's an overrun, and you can discuss that. You can discard the data and restart. Maybe you get a new reading. So we also have the head of conversion. This is for the regular channel. So whenever an ADC has been initiated to read the ADC, at the end of the conversion, you can be notified and you can read the head of conversion register. We also have the head of injected conversions. This comes from the injected channels. And we also have interrupts, the override internal interrupts. And we also have the interrupt enable for the watchdog. And you can see this goes to the NVIC systems, which handles or which manages the all the interrupts. So for our demo today, we're going to read the ADC from a potentiometer, and this is how I'm going to connect. We have the nuclear board, the nuclear F446RE, and you can see that we also have the potentiometer. I have the B10K, and one side of the potentiometer I have connected it to 3.3 volts, and the other side we have connected to ground, and the middle pin, which we call the sweep, I have connected to pin PA0. So after looking at the data sheet of your board, you'll find that for my nuclear F446, the VDD to the V reference is connected to 3.3 volts. So that's why I'm not connected to 5 volts. Just to ensure that our V in is within the VREF. So I've already connected this. Let me now go to STM32 CubeMX. And just to show how to get over with the settings, you can select each of these ADCs. So we have so many channels here at our disposal. You can select input, ADC input channel 0, and you can see this is configured to pin PA0. So if I click on this pin, you'll find that we have ADC1 input 0, ADC2 input 0, and ADC3. That means this one pin you can use to, or you can configure it to read from different ADCs. So we also have something like pin PA4. It can only serve two ADC, that is ADC1 and ADC2. So if we go to the configuration part, we have the prescaler. So the prescaler just divides the PCL clock by any of these scale, and you can see that we have the PCL clock here coming from the APB2, and right now our ADC runs at our clock to the ADC is 84 megahertz. So when we get divided by 4, so that means it's 84 divided by 4. So that means our ADC is running at 21 megahertz. And for the bit resolution, you can select either 6, 8, 10, and 12. So I must say that the higher the bit resolution, the higher the accuracy. So we have several, we have two data alignment modes, that is the right alignment and the left alignment. So just to comment on the right alignment is that it has high resolution and precision because they can resolve smaller voltage changes, and also they are susceptible to noise. So for the left alignment, they have high precision and speed. So they are faster and they can provide high precision for more significant bit. So for the compatibility, you might want to check your peripheral, whether it supports the right alignment or the left, just to make sure that you comply to the datasheet. So for the scan conversion mode, so this is whereby if you have set so many channels, you can just enable the scan conversion to get to read more than one channel. So for the continuous conversion, so just as it is, it's continuous. So when you start it, just keep running. So you have the discontinuous mode. This is one shot mode. You just run the ADC once, get the readings, and that's it. So the DMA request. So you realize that you cannot enable the DMA request at this point because you have not added a DMA request. So if I add the DMA request, then if I come back to the parameter settings, I can now enable the DMA for my ADC1. So we have the head of conversion selection. So if you have more than one channel, you can select the head of conversion flag at the end of single channel conversion, or this flag will be set when all the conversions have been made. So we have the regular conversion mode, and you can see right now we have one because we only have pin PA0 connected to ADC1. We can also add others. If I select input 1, I can just come here and say that this number of conversions, I need them to be 2. And you'll see that we have now rank 1 and rank 2. So rank 1 is how these will be done. Now you can see that we have an error. Since we have more than one channel, you cannot have the scan mode conversion disabled. So we must enable that. So for the ADC regular conversion mode, we now have 2 conversions, and the external trigger conversion is now configured to be launched by software. So you can just write a code to start the ADC, or you can control this using the timer 1, the timer 2, timer 4, 5, 8. So for the edge, now let's keep it at none. For these 2 ranks, if I expand on this, you'll find that you can select each of these channels. Just because you have selected input 0 and input 1 doesn't mean that whenever you run the ADC, you have to start getting the values from 0 to 1 going up. You can also invert depending on your priority. So I can say that the first reading I want is from channel 1, and for the rank 2, I can set this to channel 0. So that it means I'll start reading from channel 1 and then channel 0. For the sampling time, we have this. You can select each of these. They have 3 cycles, we have 15 cycles, up to 40, up to 480 cycles. So I will suggest that if you have 2 different channels and you're using the scan conversion mode, make sure that you select different clock cycles, and also make sure that the end of conversion flag for the single channel is selected. So you can also have injected groups. So for the injected groups, these are triggered. They can also be triggered by software. So if I can add another ADC, I can come to injected and select the conversion to be 1, because now I want to configure the ADC1 input 2 as an injected channel. And you can see that you can also select the trigger. So these triggers means that you can select either to be launched by hardware or software. So, and we can also see that we have the rank also for the ADC injected conversion mode, and just to select another channel, I can add this also to the injected conversion by just implementing this. And you can see that now we have two channels. You can select channel 2 as an injected conversion mode, and also channel 3. And you can be able to now get the readings from either the conversion mode, that is the regular, and the injected. So we also can enable the watchdog mode, and you can see that we have the high threshold and also the low threshold. And if you want to select the interrupt mode, then you can do so. So let's now get to the demo. So pair all the pinouts. And I'm going to select pin. I'm going to select ADC1, input channel 1, and I'm also going to select input 2, channel 2. I mean ADC1, channel 2. So I can have the first one as a regular channel, and also have the second one as injected channel. So let me have one here, and I'm going to select channel 2. I'm going to give these 15 cycles, and for this one is channel 1. I can just maintain to 3 cycles. That's okay. So also you can enable the interrupt if you want to use the interrupt method. So let me just generate this code. And the first thing that I always do is to run to make sure that no errors in importing the libraries. So let's go to user code begin 0, or we can just have a public variables here. We have the ADC1. I will call these, this is from the regular channel. And we can also have an injected a variable to hold the injected values. So we can do this using several methods. First, you can do using the polling method, you can do using the interrupt method, and you can do using the DME method. So for this case, I'm going to use the polling method. So the API is to start the ADC. So it's HAL ADC start. And this is, I'm starting the ADC1. And again, when you start the ADC, you have to wait for it to do the polling and the conversion. So you have an API to do that. So poll for conversion, and this is from ADC1. And you can specify the timeout. So we can give it all the time to do the conversion by giving it the maximum delay. And finally, if you want to read the data, I'll get my variable here from the regular channel. And I'm going to convert. Okay, no need to convert. I'm going to use the HAL ADC get value. They are getting this value from ADC1. So we start the ADC, then you poll for conversion, and then when the conversion is complete, get to read the data. So let me build this code. make sure you don't have errors, and I'm going to load the code to my board. I'm going to go into debug session and also add this to watch expression. So let's run the code, and you can see that you have different or random values coming from the ADC. So I'm going to connect my potentiometer to the ADC one. And you can see that we have now the lowest value, which is 0. If I vary my potentiometer, this value will increase up to 1495 because these are 12-bit resolution ADC. So you can also do the same for the injected channel. Let's start the injected channel. So ADC EX injected start, and this is from HADC1. Then we have the ADCX get off for conversion from ADC1 also. And let's give also the maximum time. Max delay. And then we can get the ADC value by using her ADC. Injected get value. So we're getting this value from the ADC also. And this ADC, you have to, okay, this function takes two parameters, the ADC channel and also the rank. So if I come back to my parameter settings, I did set the rank to be 1. So I'm going to have this one. So if you have more than one injected channel, you can just select the rank that you want from the rank that you want to read. So let's also build this and load this code to the board. I'm also going to have this added to the watch expression to watch one. If I run the code, you can see that we have different values. So the first one is from the regular channel, and the second one is from the injected channel. So you can also do this using the interrupt method. So maybe we can just do one for the regular channel. And we are going to start the ADC. ADC start with IT. And this is HADC1. And whenever this conversion has been completed, we shall have a callback function that will be notified that the conversion is complete. So we have this one. And we shall copy this at user code begin for. So this is HAL ADC conversion complete callback. Okay. So we can be able to get our reading from this point. And I can say ADC, let's have the regular, is equals to HAL ADC, get value. And I'm getting this value from HADC1. or simply I can just pick this. So when I get the reading, I can also restart the ADC to make sure that every time at the end of every conversion, restart the ADC. So let's do this. So I just want to make sure that I did select the interrupt for the ADC. Let me load this code to my board. And then let me add a breaking point at this point and start running the program. You can see that this function has been called after the end of the conversion, and we are ready to get the data. So let me continue, and you can see that we are also getting the ADC values by using the interrupt method. So in a similar way, that is how you do, or you can configure the DMA, and you can also configure the DMA complete transfer callback. I can be able to get readings at the end of conversion. So for the polling method, you'll see that you are engaging the CPU so much because you have to keep checking the peripheral all the time. And now using the interrupt method, you can now put your main, your other code in the while loop, since the interrupt will take care of getting the ADC values. So applications of ADC, they are widely used in the communication system, in the studios where we have the radio presenters, the voice is analog, and this data is fed to the analog to digital converters to convert the analog signals to digital signal, and same data is fed to the transmitters or the digital transmitters. So for the audio processing, like I said, for the sigma delta, widely used in the audio processing, the codecs. For the measurement and instrumentation, this is where you find things like the current sensors that gives an analog output. We have the temperature sensors. If you want to read some temperature value, like from the LM35, gives an analog output that is how do I say, proportional to the voltage. Okay, so it's also used in the medical instruments like the magnetic resonance imaging and also the CT scans to convert the analog data to image that they can be interpreted by the medical professionals. So that's all for today. Thank you for being at DevHead.